on cryptography and meta complexity, and Taiga is going to give the talk.
Thank you for your introduction. My name is Taiga Hiroka. On this talk, I talk about quantum cryptography and meta complexity. This work is joint work with Tomoyuki Morimae. Now let me explain background. In classical cryptography, one-way function is minimum assumption for cryptographic primitives. One-way function is a function f which can be computed f of x from x easily, but hard to invert x from f of x. We can construct several useful primitives from one-way function. Furthermore, for constructing these primitives, one-way function is also a necessary assumption. Given these characterizations, one natural question is to ask about quantum case. In other words, is one-way function also a necessary assumption for quantum cryptography or not? Recently, many works study this question and show the possibility of quantum cryptography without one-way function. First, pseudo-random state generator was introduced. This primitive can be seen as a natural quantum extension of PRG, where quantum algorithm outputs a pure state which is indistinguishable from truly random pure state. We can construct this primitive from one-way function, but it is an open question how to construct one-way function from this primitive. And in fact, there exists a separation. Another example is quantum cryptographic primitive with classical communication. In this kind of quantum cryptographic primitive, each party has a quantum computer, but communication between each party is classical bit string. We can construct this kind of primitive from one-way function trivially, but it is an open question how to show the other direction. And in fact, there exists a separation between them. So currently, we have many candidates of quantum cryptography without one-way function. Given this possibility, one natural question is to ask about a minimum assumption or necessary assumption for these primitives. Although there are several candidates, one natural candidate is one-way puzzle, known as one-way puzzle. In fact, from almost all of quantum cryptographic primitives whose outputs are pure states, one-way puzzle is a necessary assumption. Furthermore, for almost all of quantum cryptographic primitives, it's classical communication. One-way puzzle is also a necessary assumption. So somehow one-way puzzle can be seen as one of minimum assumptions in the field of quantum cryptography. The definition of one-way puzzle is as follows. A one-way puzzle consists of two algorithms, sampling algorithm and verification algorithm. The sampling algorithm is a quantum polynomial time algorithm that outputs a pair of puzzle and answer. The verification algorithm is an inefficient algorithm which takes puzzle and answer and outputs 1 or 0. The correctness guarantees that the verification algorithm outputs 1 with high probability over the sampling algorithm. On the other hand, the security guarantees that for any quantum polynomial time adversary, a given puzzle, it is hard to find a star such that the verification algorithm outputs 1. So this can be seen as a natural quantum analog of one-way function. And in fact, if the sampling algorithm is a classical polynomial time algorithm, then that kind of one-way puzzle can be shown as equivalent to one-way function. So one-way puzzle can be seen as a natural quantum analog of one-way function. Given that one-way puzzle is one of minimum assumption, natural question is from which assumption can we construct one-way puzzle? Currently, it is known that the existence of one-way puzzle implies that PQP is not equal to PP. So constructing one-way puzzle unconditionally seems extremely challenging. So given that, natural question is to construct one-way puzzle from that BQP is not equal to PP. This question can be seen as a natural quantum analog of constructing one-way function from that P is not equal to NP. In the classical case, this question has long been an open question, and no one succeeded in proving this conjecture. And in fact, there exist several proof technique limitations. On the other hand, recent work studies the new technique called meta complexity and show some nice result for showing this conjecture. So let me explain the recent progress about meta complexity. Roughly speaking, meta complexity is a complexity of problems to ask for complexity. For constructing one-way function from that P is not equal to NP, while there are several proof technique limitations. But sometimes there are examples to overcome this kind of barrier by using the technique of meta complexity. That's one of the reasons why many people study the meta complexity. And furthermore, we can give a characterization of one-way function, and P is not equal to NP by meta complexities. First, it is known that one-way function can be characterized by several average case hardness of meta complexity problems. Furthermore, worst case P is not equal to NP can be also characterized by several worst case hardness of meta complexity problems. So in order to show one-way function from that P is not equal to NP, it is necessary and sufficient to show the worst case to average case reduction within meta complexity. Given this background, currently it is considered as an important subject to study meta complexity for showing one-way function from that P is not equal to NP. On the other hand, before our work, all of these characterizations are known in the field of classical cryptography and classical computational complexity. So one natural question is to ask about quantum case. So in our work, we study this open question and show give a first characterization of quantum cryptographic primitive by meta complexity. Note that there exists a concurrent work which obtains similar result. Now let me explain our main result. In our work, we show that one-way puzzle is equivalent to quantum average case hardness of gap K problem. Informally, this is the assumption that estimating Kolmogorov complexity of a classical bit string generated by quantum algorithm is hard on average over the quantum algorithm. Now let me explain this notion in more detail. For this, first I will explain the notion of Kolmogorov complexity. Kolmogorov complexity is defined for each classical bit string. Informally, Kolmogorov complexity of a bit string X is defined as the minimum length of program that prints the bit string X. For example, let me consider the X1 and X2 as an example. X1 is a bit string that repeats 0 for many times. In this case, if we want to output X1 as a program, it is sufficient to write repeat 0 for X1 times. So the Kolmogorov complexity of this kind of bit strings becomes small. On the other hand, if the bit strings is random and there is no way to compress these bit strings, we need to include every information into a program. So the Kolmogorov complexity of uncompressible bit strings becomes large. So in this way, somehow Kolmogorov complexity captures information which is contained in classical bit strings in a clever way. In our work, we study the computational complexity of estimating this notion, this value. So our assumption is quantum average case hardness of gap K problem. This is assumption that there exists a quantum polynomial time algorithm Q, which outputs a classical bit string X. As a security, we declare that for any quantum polynomial time algorithm given X, it is hard to decide if the Kolmogorov complexity of a bit string is small or large. So this is a rough definition of quantum average case hardness of gap K problem. We show that this assumption is actually equivalent to the existence of one-way puzzle. Note that in the classical case, a similar result is known. In the classical case, it is known that one-way function is equivalent to the classical average case hardness of gap K problem. Here the difference is that they just consider a classical polynomial time algorithm instead of a quantum polynomial time algorithm. Our result can be seen as a natural quantum generalization of IRS-22 result. Now let me explain the technical overview of our result. So given that our result can be seen as a natural quantum analog of IRS-22, one might wonder if our result can be obtained by a straightforward adoption of the IRS-22 technique. Actually, the answer is no, and we need novel idea for generalizing their technique into the quantum setting. So to explain it, let us recall the IRS-22 approach. First, in their work, they consider PRG, which can be constructed from one function. Then from PRG, they show the hardness of gap-K problem. And roughly speaking, the output of PRG has small Kolmogorov complexity because output can be described by short length of random seed. So if we can estimate Kolmogorov complexity, we can break arbitrary PRG security. So that's the reason why we can show this direction. And for showing the other direction, they consider average case hardness of estimating classical probability distribution. This is the assumption that there exists a classical polynomial time algorithm C, such that on average, over the algorithm of C, it is hard to estimate this value within multiplicative error. From this assumption, as shown by Impagliazzo and Levin in 1990, we can construct one-way function. So they show that how to obtain this hardness assumption from classical average hardness of gap-K problem by using the technique of Kolmogorov complexity. So informally, this is a approach by IRS-22. So we naturally think about quantum analog of them. So we consider quantum average hardness of gap-K problem. And instead of one-way function, we also consider one-way puzzle. And we also consider estimating quantum probability distribution. Here the difference is that we consider quantum polynomial time algorithm instead of classical polynomial time algorithm. And we also have some kind of analog of quantum PRG, quantum version PRG. This is slightly different from the original PRG. In particular, this QPRG does not have random seed, but as a security, we require that the trace distance between this and the uniform distribution is statistically far and computationally indistinguishable from uniform distribution. Fortunately, we can construct this non-uniform variant of this kind of primitive from our puzzle. On the other hand, we cannot apply the classical technique because importantly, QPRG does not have a random seed. So we need to introduce idea for showing this direction. And actually, most challenging part is to show the other direction of constructing one-way puzzle from quantum average hardness of gap-K problem. Fortunately, this direction, so showing average case hardness of estimating quantum probability from quantum average hardness of gap-K can be obtained in the same way of IRS-22. But the most challenging part is to construct one-way puzzle from average case hardness of estimating quantum probability distribution. This is because in the classical case, their technique heavily depends on the fact that a classical algorithm has random seed. In particular, roughly speaking, in their technique, assuming that there do not exist one-way function, then they show by using the Stock-Meyer's technique, they show how to estimate this value within multiplicative error. So by counting the number of the random seed. But in the quantum case, we do not have a random seed, so we cannot adapt the technique of Impagliazzo and Levin in the quantum setting. So we need to introduce idea for solving this problem. So now let me explain the brief sketch. First, in our work, we consider distributional one-way puzzle, which can be seen as a natural quantum analog of distributional one-way function. Distributional one-way puzzle is a quantum polynomial time algorithm SAMP, which outputs a pair of K and S. Roughly speaking, as a security, given S, no quantum polynomial time adversary can simulate the conditional distribution of the sampling algorithm. It is on that we can construct one-way puzzle from these primitives. So our main contribution is to construct distributional one-way puzzle from the hardness of estimating a quantum probability distribution. Okay. So let me explain the brief sketch. In our work, we show the contraposition of this direction. So assuming the non-existence of distributional one-way puzzle, we show how to estimate quantum probability distribution on average within multiplicative error. First, we observe that this value can be divided into the following each conditional probability. Here, for the simplicity, I consider the case where the quantum algorithm outputs only 3 length classical bit strings. And by using the non-existence of distributional one-way puzzle, we show how to estimate each term within additive error on average. So the goal is to estimate this value within multiplicative error, but in the average case, we show that additive error estimation is actually sufficient for multiplicative error estimation. In this way, assuming the non-existence of distributional one-way puzzle, we show how to estimate quantum probability distribution. Note that there exist 2 concurrent works which obtain similar results for showing this direction. Now let me summarize my talk. In our work, we show that one-way puzzle can be characterized by quantum average case hardness of gap problem. So one natural question is to ask about computational complexity of them. So in particular, for the existence of one-way puzzle, PP is not equal to BQP is necessary. So one natural question is to give a characterization of these notions by metacomplexity. In the classical case, these analogs are shown, but their technique heavily depends on that their language are NP or some other classical techniques. So it is quite non-trivial to obtain these results. So this might be interesting open question. Thank you for listening.
We have time for a few questions. Okay, if not, I'll ask a question. So have you thought about other connections between other quantum cryptographic primitives and their connections to metacomplexity?
That's a good question, but I consider the quantum state setting, but it is quite non-trivial to define cosmograph complexity of quantum states to me. So I'm not sure how to obtain these kind of characterization. So I would like to characterize, for example, EFI by quantum metacomplexity, but metacomplexity for quantum states is non-trivial to define. So it is unclear to me.
Okay, if there are no other questions, then let's thank all the speakers for this section again. Thanks everyone for coming.